What's up, everybody? Welcome back to another live stream from the Scalar Learning channel. And today we are back at it with Critical Concept Lecture 4 of 4. So this is our final day of the Critical Concept series for this J.E.D.I digital SAT class. By the way, I'm just doing a quick thing where I'm just making sure the stream's looking great. All right. So we are ready to go. And by the way, thank you guys for jumping on and getting here ahead of time. Oh, by the way, Lucy, can you post something in the J.E.D.I board as well for school? So we're just going to make sure people have the link on the platform. But first of all, those of you who are here, I assume you guys are already on our school platform, that's SKOOL. If you're not on the platform, I advise you to join. That's where you can get all the resources and the slides and all that stuff. And everything is free. You also get the calendar with the assignments and all the notifications of our schedule and the planned classes and all that good stuff. You might also be aware that our verbal classes are on Thursdays, math is on Tuesdays. But again, thank you for joining along in this really fun journey, and welcome back if you are coming back, and welcome if you are new to these streams. So today, what's up, Osama? What's up, Robert King? You're very welcome. What's up, Matthias? Great to see all of you again. You guys have been regulars following along. Super cool to have you back. So today we are going to be talking about geometry and trigonometry. And I know this is a topic that a lot of students always seem to be asking about. I think one of the reasons why is because a lot of times geometry and or trigonometry, but especially geometry, is taken earlier in high school, sometimes before you're taking the SAT. So then you know, students sometimes forget some of the concepts in the material, have to go back and relearn it. You might understand it perfectly fine, but it does create that issue because it's usually a little bit further back in the curriculum with respect to when you take the SAT. So we're going to go over everything today, and we're also going to talk about the things that are given on the formula sheets. That's also very important as well. By the way, if you could, what's up, Muella? If you could, in the chat, if you guys are here now, make sure to post in the live chat where you guys are from in the world. I'd love to know that. And so far, if you could also let me know of the class and of the website and of the lectures and all the good stuff, what have been your one or two most valuable lessons or most valuable videos or most valuable things in general that you've been able to take away from this course? I'd really love to know. That would be super cool as we get started. So I'm going to be checking out, hold on, let me just move this around here on my screen so I can see this a little bit better. Okay, there we go. I'm going to be checking the chat window. There we go. I'll be checking the chat window for those responses and also answering questions on the fly as we go through. That's going to be the benefit of you guys joining along with the live. If you guys are watching the replay after the fact, no worries. You can post your questions in the comment section, and I'll do my best to get back to you ASAP. All right, without further ado, last but not least, if you guys are looking for the best resource for SAT practice tests, make sure to check out right up top the SAT crash course. These are amazing practice tests that are modeled after the College Board tests. I've also partnered with them officially. You can also see all my video explanations for every single math question from practice tests 1 through 10. That's module 1, module 2, lower and higher difficulty. So I've done one for everyone. That's 66 questions per test. So make sure to check that out. Osama says he is from Egypt but lives in Katy, Texas. It's really, really cool. I was in Texas last year, actually, in Dallas. So great area, great state. Okay, let's get into it. Here we go. Starting off, we got geometry and trigonometry. And there's going to be 6 subcategories underneath geometry and trigonometry. First, we're going to have area and volume. We're also going to have congruence, similarity, and angle relationships. So we're going to talk about what does congruence and similarity mean? What are the angle relationships that we have to know and understand? Right triangle trigonometry, that's also going to include stuff on Pythagorean's theorem, as well as special right triangles, which are kind of like the foundations of a lot of this trig material that you're going to have to know. Circle theorems, theorems involving circles, and unit circle trigonometry from TNT. Oh, Trinidad and Tobago, Lester, welcome. That's cool. Very cool. And for unit circle trigonometry in particular, people ask me a lot of times, hey, do I need to know the unit circle for the SAT? I generally say, no, you don't need to know it. There's ways around it. But it is a little bit nice to have it in your back pocket if it's not a huge burden to just get it back in your memory banks and like kind of understand what it's about. So we're going to talk about it today, and I'm going to explain it in broad strokes. And then I'm going to also show you how to work around if you do forget the unit circle or have a hard time memorizing it. Muella is from Zambia. Amazing. Halfway across the world. Very cool. And the category number 6 is circle equations, okay? I also have a song on circle equations. I posted that in the school website as well. I live in California. Okay, so 1 second. Let me post this school thing here. So here's the link. If you guys haven't joined, make sure to click this link and join our class. I think we have 279 members as of this morning. So it's growing and growing fast. It's going to grow a lot probably in the next couple weeks as we get close to the actual SAT on August 24th. So very exciting. And without further ado, let's get into it. All right, starting off with area and volume. So I'm going to start with the given formulas because this is very important. You should know what's given and you should know where to find what's given. Now, the beauty of the digital SAT is you don't have to flip back to the front to find these given formulas. There's always going to be a button up top as you're taking it where you can click the reference sheet and this will pop up at any time. So we want to know what's on here, and you can see some really cool stuff, right? And I'm still going to go over these formulas in other slides, some of them. But, you know, we have area and circumference of a circle. We have area of a rectangle, area of a triangle. Here is Pythagorean's theorem. I'm still going to parse it out for you guys because I want to talk about how to use it and apply it. Also, I'm going to talk about special right triangles, even though that's given here as well. Then we have volumes for these 5 solids. I'm going to go over these as well, just so you can understand what each component is, if this is a little confusing. And I'm also going to talk about surface area, because surface area continues to show up. Now, it's probably going to be a little overkill on surface area. There's going to be some formulas that I'm going to give you that you may likely not need, and I'm going to tell you why, because you can deduce a lot of these formulas. But I'm going to show you them anyways, just in the case that now the College Board decides to integrate some of these surface area things in. Now, I know SAT Crash Course, for example, has asked a question about the surface area of a pyramid. I haven't seen that on a real SAT yet, but I could see it coming up, and I could see it coming on there. So we're going to talk about how to deduce that formula, as well as deduce that process, I should say. Or I'm also going to give you the formula for surface area of a pyramid and show you how to do that. Also, remember here, they tell you the number of degrees in a circle is 360, and the radians is 2 pi. That right there tells you that 360 degrees is equal to 2 pi. So if you ever need to convert between radians and degrees or vice versa, you have the equivalency right here. Okay, so just remember that. All right, let's get into our volume formula. So again, this is given, this is the sphere. If this is the radius, which is all you need to know for a sphere, it's 4/3 times pi times radius cubed, okay? For a cylinder, it was like a can of Coke. The volume is pi r squared, that's radius squared, times the height, that's in red, right? So with this color coding might make it a little easier to see what they're talking about. A prism could either be a rectangular prism, a triangular prism, we could have a hexagonal prism, we could have all sorts of prisms. What is a prism? It's basically taking a 2D shape. It could be a triangle, a rectangle, a hexagon, a pentagon, and then stretching it out, right? So what we see here is a triangle stretched out, hence a triangular prism. What we see is a rectangle here stretched out by the height, hence a rectangular prism. So how do we find the volume in general? Well, we take the area of the base. So whatever that base might be, here it's a triangle, use the area of a triangle formula. Here it's a rectangle, length times width, and then multiply that by the height, by whatever value you're stretching it out by, and you get your volume. We also have 2 other volume formulas. We have volume of a pyramid. Okay, again, this is on the reference sheet. And you can have, again, a hexagonal pyramid, a square pyramid, all sorts of different pyramids depending on the base. And to get the volume, it's 1/3. That's an important number that crops up again with cone. 1/3 area of the base, whatever base that is, times the height. And a cone is very similar. Right, here's a cone, it's a circle base, and then it goes up to the top, kind of like a pyramid. So it's sort of like a circular pyramid. And that is, again, 1/3. So again, a point on the top, you should remember 1/3. 1/3, and really it's the same thing. Area of the base is pi r squared because it's a circle base. Pi r squared, area of a circle, times the height, that gives it the volume. So you see similarities between these two. Now, let's talk about some surface area. This I've seen once, and it may have been on a non-College Board practice test, so I don't know if this is critical, but I wanted to give you the formula anyways because it's not on the reference sheet. Surface area of a sphere is 4 pi r squared, okay? Surface area of a cylinder is 2 pi r squared plus 2 pi r times h. Now, you can also deduce this because where am I getting this from? 2 pi r squared is the circle on the bottom and the top. That's just area of those two. What's 2 pi r times h? 2 pi r, if you remember, is circumference going around the top. So it's basically the circumference times the height. So it's the area of the circles doubled, right, because it's 2 of them, plus 2 times, I'm sorry, not 2, let's just say the circumference, which is 2 pi r, times the height. And then a prism is whatever the height is. Again, it's the perimeter of the base, whatever that may be, times the height, plus 2 times the area of the base. Now, that's fine, okay, if you want to memorize it that way. Or you can just think about it as, wait a minute, I got 6 faces here. I got 2 rectangles here, 2 rectangles on the front and back, 2 on the top and bottom. Let's just calculate the area of each and add them up. That is totally fine. That's probably going to be your most likely case for a surface area question, but I'm giving you the other options. For this one, again, it's 2 triangles and then 3 rectangles, so you can calculate them individually. That's actually, honestly, what I do. I feel like that's easier, but I just want to give you the option. Okay, then we also have surface area of a pyramid. Okay, so this is 1/2 the perimeter of the base, whatever that may be, times the slant height. What's the slant height? These faces that are slanted, it's like if you look at that as a 2D shape, like this is a 2D triangle, and what's the height of that triangle? And you notice it's slanted, that's why they call it a slant height, versus the straight up and down vertical height. And then plus the area of the base, okay? And for a cone, this one is the one that's, I think, the hardest to remember because it's a little different. Pi times radius times the slant height plus pi r squared. Again, I haven't seen one where they're asking the surface area of a cone. I don't think it's super likely. I wanted to give it to you just in case, but I would put it low on the totem pole priority. Okay. Now, area formulas, they're giving you a lot on the reference sheet, so there's not too much to worry about. One that they didn't give, which I have seen pop up on the SAT, is the area of a parallelogram, which is pretty straightforward. Sorry. It's pretty straightforward. It's base times height. How do I determine these? The base is whatever side you want to choose, and then the height is from the opposite side coming down and making a right angle, aka being perpendicular. Then we also have a trapezoid, which I haven't seen in a while on a digital SAT, but just in case, I've seen it definitely before on older versions. For the area of a trapezoid, it's 1/2 base 1, which is the top base, and the bases are the 2 sides that are parallel, right? 1/2 base 1 plus base 2, and then times the height. And again, the height is the distance between the 2 bases. Okay. That does it for category 1. So now we're moving on to category 2. All right. By the way, guys, for those of you who are on right now, if you could click that like button, it really helps the video and the channel and all sorts of stuff a lot. And so if you could click that button really quickly, I'd really appreciate it, especially if you are enjoying or finding this useful. All right. Let's move it along to congruence, similarity, and angle relationships. Okay. First of all, what is congruence? What does it mean? Actually, somebody answer that for me. What does it mean? Fortnite Sweaty Kid says surface area aren't tested. If they do, there's a 1% chance. Well, it's higher than 1%. I don't know. Why do you get 1%? Because they've had some really difficult surface area like, what do you mean by that? Do you mean that yeah, everything is equal? Good job. That's exactly what congruence means. What do you mean 1% chance? Do you mean 1% chance 1% of the problems are going to be surface area? There's a 1% chance it shows up on a SAT. Because if it's the latter, that's definitely wrong. But if it's the, yeah, Matthias, I'm pretty sure. I mean, I don't know because I don't know what was on the May SAT, but I know in the practice test for the College Board, definitely it shows up. Yeah, I don't think that's correct. You're saying 1% chance surface area problems will show. No, I've seen them on multiple practice tests. So I mean, even if I've only seen them on one, that's 1 out of 6. That's more than 1% chance, substantially more. But if you don't want to study it, I mean, more, all good. It's not going to be a lot. I'll tell you that. It's not going to be a lot. Okay, so congruent means that everything is equal, okay? So what does that mean? So it means that 2 shapes are identical. So if I have a pentagon here, I'm going to have the exact same pentagon, and then those 2 pentagons are therefore congruent. And moreover, what does that mean? That means every corresponding side is equal, and every corresponding angle is equal. Everything is equal to everything, no difference. Versus similar. What does similar mean, or similarity? Similar just simply means proportionate, okay? So one example is like, think about a Xerox machine where you're like blowing something up, or you're scanning something and you're blowing the image up, expanding it. So everything is proportionate, so it looks the same, but, the side lengths are bigger. What about the angles? The angles are actually identical. So similar shapes, the side lengths are different but proportionate, but the angles are identical. They love to test on this. They say, hey, two of these shapes are similar, right? There's a 1:3 ratio in terms of the side length. And then if a corresponding angle is 30 degrees, what's it in the similar shape where it's a 1:3 ratio for the side lengths? They're trying to trick you into saying 90, right? 3 times 30 is 90, but that's incorrect. The angle, even though there's a 1:3 ratio for the sides, is still congruent. So it's still exactly. Osama says the same. It's still the same. So again, here you can see similar is proportionate. All right. So the two things for similarity, sides are proportionate, angles are congruent. Our HL theorem going to be on the SAT. Yeah. We're going to talk about, great question, Fortnite 20 Kid. We're going to talk about hypotenuse leg. I think I'll put it like this. It's fair game, and I have seen it definitely on the SAT. Is it going to be the most commonly tested congruence theorem between two triangles? Probably not. Again, I am saying that based on a fairly small sample size of 6 practice digital SATs. But from my recollection, I feel like ASA, side, 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 and side, angle, side, those are probably the most commonly tested. Actually, angle, angle, side, too. I mean, I would just know all of them. There's only 5. It's tough for me to say exactly which one is going to be the most commonly and least commonly tested, but I would definitely know hypotenuse leg. It's not that bad. We're going to talk about it when we get to those theorems. Okay. All right. Now, congruent triangles. Here we go. Fortnite 20 Kid, you are ready to go. Check out the 2023-2024 DSAT. What's that? I'm not sure what that is. If you're talking about the practice tests, I've seen them all, but I don't know if you're talking about something different. I just got to know them. Doesn't matter what's commonly yeah, exactly. You should know them. Okay. Okay, so the 5 theorems for congruent triangles are side, side, side. So if you can prove that all 3 sides are congruent, you're done. The triangles are congruent, meaning the rest of the angles are all congruent as well. Next, side, angle, side. Very important that the angle in question is wedged between the 2 congruent sides. For example, if my angle was over here that was congruent, that would be angle, side, side. Also spells ASS. That's a good hint that that's not a legitimate theorem. Okay, ASS is no-go, but side, angle, side is legitimate. Side, angle, side in that same order. We also can see that if we have an angle congruent, then a side right next to it, then an angle right next to that, that also shows 2 triangles are congruent. Angle, angle, side. Okay, so we have 2 angles and then 1 corresponding side. That's a legitimate way. And last but not least is hypotenuse leg, which is if we know that they're right triangles, meaning they both have a right angle, then as long as you can show that just the hypotenuse and one of the legs are congruent, the triangles are congruent. So Fortnite 20 Kid, if you are talking about, I'm not sure what you're talking about. You may be talking about something that is not officially released, meaning those are not, that's not legal. If it's something that's not released, that's not legal to look at. So we can't talk about it on this chat or anywhere, honestly. We can only talk about the practice stuff that the College Board has officially released. Are you referring to released it? I don't even know what they've released. I think they've only released practice tests. I don't think they've released any of the actual official digital SATs. That's my understanding. All right, so moving on. After hypotenuse leg, now those are the 5 congruence theorems. What about similar triangles? And a lot of times they'll be like, hey, these 2 things are true. What's the third thing that we need or the second thing that we need to show that these 2 triangles are similar? Are you guys going to publish DSAT calculator programs for test day? It's not on my list. The main reason is because the main calculator that I've been talking about is Desmos. But if that's something that you guys are super interested in, let me know. Okay, a side note. I have something for you to research seriously with Dan over there. I'd recently received an email from Testive that guessing is now penalized. I have not heard that. I don't know if that's true because I just had a meeting with the College Board back in June. Not me, but the National Test Prep Association. They said nothing about that. They did say that certain questions might count for more points on the math section. If they're now penalizing for guessing, that must be a new thing. that I haven't heard, or it might be a mistake. I am thinking that's a mistake. But I don't know. So, share it with me. Send it to me. All right, so similarity in triangles. This is the most commonly tested from my general experience of the SAT is angle similarity. If you can show that two angles in two triangles are congruent, they're similar. Done. Don't need anything else. You can also show side angle side. Now, this is not side angle side of congruence where you have two congruent sides and a congruent angle in the middle. These are two sides that are proportionate, right? If you can show AB over XY is the same as AC over XZ, they have the same ratio and proportion, and the angles in between those proportionate sides are congruent. Now we're talking similarity. Last but not least, side, similarity, not congruence, which means that all three sides are proportionate in the exact same way. You know that these two triangles are similar. Okay, so let me see what you guys are saying. Scoring algorithm assesses how a student guesses. Yeah, Lester, if you guess a lot of questions, even get it right, I don't know. You're talking about the College Board having a way to assess guessing. I don't know. I mean, they haven't disclosed anything like that to us, and that was not too long ago, unless it's a brand new feature. I feel like I just feel like I would have heard about it because I talk to a lot of people about this test all the time. I have heard, so Fortnite said, what happens if you answer questions way too quickly? I have heard nothing about being penalized for answering questions too quickly. I could see that as being a barometer for like, oh, you guessed because you answered this really hard question in 3 seconds. I mean, I could see that, but see, that's a slippery slope. That's a very slippery. Think about it. What if you were able to figure out a question in 5 seconds or 10 seconds with a shortcut, something like that, and then they're marking that as a guess? Like, think how unfair that is. I just don't buy it. I don't buy it. I think that's bad info. Okay, moving on. Triangle angle sum theorem. Now, this is technically on the reference sheet because it does say at the beginning, all the angles in a triangle add up to 180 degrees. But just so you can see it again, if we have a triangle and those are the angles, they always add up to 180. This is essential. You got to know this. Probably most of you do know this. Now, if we have a right triangle, this is even cooler because right triangle means one of the angles is 90. What does that mean about the other two angles if they all add up to 180? That means the other two angles must be adding up to 90, aka complementary. We're going to talk about complements and supplements in a second, but they add up to 90, and that makes sense, right? But again, just something to keep in your brains. Okay. So what are complements? What does that word mean? When two angles are complements, it means they add up to 90. So an example would be, right, X and Y here. You know that X and Y together make that 90-degree angle. They could be 15 and 75. That's one example because those add up to 90. They could also be 30 and 60. Okay. What about supplements? Right? Supplementary angles. Those are angles that add up to 180. If you're having trouble keeping track of those two, think about C comes earlier in the alphabet, hence it's the smaller number, 90. S, supplements, comes later in the alphabet. It's paired with the bigger number, 180. So again, this would be a straight line angle is 180 degrees. So any two angles that's called a linear pair, W and Z, when they form a straight angle together. But those two angles are supplementary. An example could be 30 and 150 or 95, 85. The list goes on and on. Okay, now we're going to talk about some angle relationships. So these two lines are parallel, right? Why do I know they're parallel? Because of these markings. These markings imply that they're parallel. Okay, so there's some really cool relationships that we need to be aware of when we have parallel lines. So first, we have something coming across, intersecting both lines. This is called a transversal. Do you need to know that term? No, but you need to know what happens with the angles surrounding the transversal touching these two parallel lines. So if I label the angles as follows, 1 through 8, we first have corresponding angles. What are corresponding angles? Corresponding angles would be like 2 and 6 or 4 and 8. And by the way, corresponding angles are congruent. 2 and 6 look congruent. So you can also use the logic test here. But the way I define corresponding angles, why are 2 and 6 corresponding? Because you basically take this angle and you slide down the transversal to the identical position down here, and it's that 6. With 4, you slide down the transversal and you come to 8. We also have 3 and 7 are corresponding. 1 and 5 are corresponding, right? That's corresponding angles, and the relationship with corresponding is they're congruent. And by the way, there's only two relationships. We're either going to have congruent or supplementary. So you can do the look test and be like, do those look equal? No. Well, then they must be supplementary, and vice versa. Now we have alternate interior angles. When we talk about interior, we're saying the inside of these two parallel lines. So 3, 4, 5, and 6 are the interior angles. What are alternate interior angles? Alternate sides of the transversal. So 4 and 5 would be alternate interior. 3 and 6 would be alternate interior. And if you had to guess, what's the relationship? Are they supplementary or are they congruent? They sure do look congruent, and that is the case. 4 and 5 are congruent, 3 and 6 are congruent. So alternate interior angles are congruent. We also have alternate exterior angles. That's now on the exterior of these two lines, aka 1, 2, 7, 8. Alternate ones would be 1 and 8 and 2 and 7. And again, congruent. So right now we've only talked about relationships of angles that are congruent. Now we get to consecutive interior angles. Again, interior, 4, 6, 3, 5, right? Those are on the interior. Consecutive, that'd be 4 and 6. Do those look congruent? No, they don't. What about 3 and 5? Do those look congruent? No, they don't. Hence, they are supplementary. So 4 and 6 consecutive interior angles are supplementary. They add to 180, same as 3 and 5. You also have the same relationship, which I didn't put down here, which is consecutive exterior angles. 2 and 8 have that same relationship. They're supplementary. 1 and 7, same relationship, supplementary. Now we have vertical angles. Vertical angles have really nothing to do with the transversal or the lines being parallel. But whenever you have a crisscross, like an X shape, vertical angles are kind of across from each other, like 7 and 6, 5 and 8, 3 and 2, 1 and 4. And this is very important. Vertical angles are always, again, congruent. So 1 is congruent to 4, 2 to 3, 5 to 8, and 6 to 7. Whoops. 6 to 7. Okay. So there we go. Let me know if you guys have any questions in the chat. All right. And we are going to keep going. Now we are on to interior angles of a polygon. Okay. This one isn't as super heavily tested on the SAT, but I'm giving it to you anyways because just in case, or if you forget how many angles are in, what is the sum of the angles in a quadrilateral or something, you can use this to figure it out. So what is this formula? N represents the number of sides of any polygon. So if we want to know the sum of the interior angles of any polygon, just take the number of sides, plug it in. So for example, if we have a triangle, we plug in 3. 3 minus 2 is 1 times 180 is 180. Now, when I say the measure of an individual angle in a triangle is 60, that's for a regular triangle, meaning an equilateral triangle, where all the sides and angles are equal. That's called a regular polygon. For a quadrilateral, 4 sides, you plug in 4. 4 minus 2 is 2 times 180 is 360. These are the two that you're probably going to have to know. So if you memorize them, cool. But again, you can use the formula to derive them if need be. And again, this is for a square, a nice regular quadrilateral. They'd all be 90. Now I've given a list of all the other ones. Again, you don't need to have these memorized by any means. You get you just basically plug this into the formula, plug in 11, and you'd get 1620. And so on and so forth. There's a dodecagon at the end. But no need to memorize these. I'm just giving you this as extra information if you do find it helpful. All right, next we get to exterior angles. All right, Cheerio has a question. For math, College Board replaced easy questions with a lot of constant questions, like they stick easy questions. Easy, what do you mean by easy? Okay. And a lot of questions take a p into the quadratic or circle equation. There's much practice for this, so what should we do? What they stick a p? Oh, I know what you mean. You're talking about like a constant, like an extra constant in there. The reason why they're doing that, in my opinion, is because, which I talked about in the advanced, I gave some examples of this. If you missed my lecture last week, you should watch it. But when they throw in constants like this, it's usually, easy, you meant easy. They're usually trying to get you not to they want to stop you, in my opinion, from just being able to plug it into Desmos and figure it out. So a lot of times in quadratics, when they have an extra constant and then they talk about the number of solutions, they're trying to direct you to use the what's called discriminant with that constant and then create an inequality or an equation from the discriminant. So it's like they're trying to get you to use these formulas that may have become needless with the advent, now that the whole test you can use a calculator. So they're trying to make it so that you kind of have to go back to them and still have to know them. That's the way that I look at it. for a circle equation when they have constants. I'm trying to think of an example like that. I think usually for the circle equations, it's like they're trying to either get you to understand in standard form. We're going to talk about the circle equation later, so we'll get there. But they're either trying to get you to understand that whatever's on the side of the radius, or the constant on the other side of the equation has to be the radius squared. And the constants within the parentheses have to correspond to the center of the circle, which we're going to talk about. Okay. Exterior angles of a polygon. Guess what? Every polygon, the exterior angles add up to 360. So that's really nice and convenient. I don't care if it's a square, a dodecagon, whatever. Okay. So here's a pentagon. All the exterior angles are 72. 5 of them add up to 360. What about a hexagon? They're all 60. Again, adds up to 360. All right, now we're going to talk about the difference between radians and degrees. Now, this is just like Fahrenheit and Celsius. They're two different sides of the same coin. So, for example, 0 degrees is the same as 0 radians. Let's skip ahead here. The most important one is that 180 degrees is equivalent to pi radians. If you remember that, or 360 is equivalent to 2 pi. If you remember that, you can always go back and forth pretty easily by using these equations, right? If you're converting from degrees to radians, take the degrees, multiply by pi over 180. If you're going radians to degrees, multiply by the reciprocal, 180 over pi. And that makes sense because 180 degrees is equivalent to pi. Some of the ones that are common, that are used a lot, 90 degrees is the same as pi over 2. 30 degrees is pi over 6, etc., etc. Now we're on to topic number 3, right triangle trigonometry. So we're going to again start with Pythagorean's theorem, which is on the reference sheet. But what is Pythagorean's theorem? It says that for any right triangle, the sum of the legs squared, A and B, is equal to the hypotenuse squared. So for example, if we have legs 3 and 4, 3 squared plus 4 squared, and a hypotenuse of 5, it should fit this equation. And it does. Because 9 plus 16, right? 4 squared is 16, 5 squared is 25. 9 plus 16 is indeed 25. So that's what Pythagorean's theorem is. And this will hold true for any right triangle. Now, what can we use it for? We can use it to find a missing side of a right triangle when we know, and only when we know, the other two sides. For example, I know the leg here, legs are the two smaller sides, right? Are 5 and 12, but I don't know the hypotenuse. Okay, well, I know it's a right triangle because I see this little right angle here. I can use Pythagorean's theorem to solve for C. And by the way, what is A and B? Doesn't matter. A can be the little leg, A can be the big leg. That doesn't matter, but C has to be the hypotenuse. So I can say leg 1 squared plus leg 2 squared in whatever order equals C squared. That's 25 plus 144, which is 169. Now, that's C squared. That's not C. So to get C, I take the square root of both sides, and we get C is equal to 13. So this is how we find the hypotenuse of a right triangle. What about if we need to find a leg? How do you okay, I'm going to get to that question in 1 second. How do we find a leg? Well, again, using Pythagorean's theorem, if I know one leg and I know the hypotenuse, I need to find B now. Could have called that A as well. We've got 7 squared plus my unknown leg squared equals 25 squared. That's 49 plus B squared equals 625. Subtract 49 and we get 576. Again, take the square root and we get B is equal to 24. All right, how do you find exterior angles of a shape? So if you need to find the exterior angle of a shape, the nice thing is if you know the corresponding interior angle, it's going to be supplementary to the exterior angle. That's one way. If it's a regular shape, by the way, this hasn't been, I've barely seen this. I don't even think I've seen exterior angles on a practice test, but I'm giving this to you just in case, because technically it's fair game. If you know it's a regular polygon, that means all the angles, interior and exterior, are equal. Since you know that the sum of the exterior angles are 360, and the number of angles is equal to the number of sides, if I wanted to know one exterior angle, that's again, if they're regular, meaning all of them are equal, I'd say, all right, let's say it's a 12-sided figure. Exterior angle would be 360, the total divided by 12, the number of angles. 360 divided by 12 is 30. Okay, so let me know if that makes sense. Okay, now we're going to talk about special right triangles. There's two of them, a 45-45-90 and a 30-60-90. Okay. Now, these are the ratios, and these are also presented on the reference sheet. And so what it tells us, and the reason why this is nice is because usually for Pythagorean's theorem, we need two sides to get a third. Here, you can just have one side and you can get the other two. If you know the angles are in this format, 45, 45, 90, 30, 60, 90. Okay. Okay, just again, let me just explain. So if I know the legs are x, the hypotenuse for this one is whatever that is times rad 2. If I know the leg here is x, I know the hypotenuse is double the little leg. And the medium leg is rad 3 times the little leg. What does this look like in practice? Okay. So I have a 45, 45, 90, and I know the legs are 3. Well, then to find the radius, okay, I see down here the legs are 3. That's x. So the radius, not the radius, the hypotenuse is the little leg x times rad 2. So here it would be 3 rad 2. Okay. So those two are matched up. Now for 30, 60, 90, if I know that my little leg is 6, and this is the key leg to figure out everything else. Like if you are given this, you should go little leg, then hypotenuse. If you're given the hypotenuse, go little leg, and then long leg. But anyways, since I know that that's my little leg, my medium leg is just a little leg times rad 3, as you can see down here. And my hypotenuse is just double that little leg, so double 6 is 12. All right. Hope that makes sense. And we're talking trigonometry. Of course, we got to talk about SOHCAHTOA. So SOHCAHTOA, what's up, Cole? Welcome, welcome. And yes, they can switch the 30 and 60 around, and the people switch that around by accident. Yeah, I can see that. So anyways, back to this. Yeah, Cole, no worries that you were late. You can definitely watch the replay. All good. What is SOHCAHTOA? This is our acronym to help us remember to use sine, cosine, and tangent. So again, S, C, and T stand for sine, cosine, tangent. O stands for opposite. H stands for hypotenuse. So this helps you remember that sine of an angle, in this case A, is equal to the opposite side over the hypotenuse. Hypotenuse is always the big side opposite the right angle. Cosine is equal to AH, adjacent side over hypotenuse. Again, adjacent relative to this angle. You might say, wait a minute, the green is adjacent to A. Yeah, but that's adjacent leg, which is orange. The green is always hypotenuse. Okay. Now we go on to tangent, okay? So tangent is opposite over adjacent, okay? So tangent of A is opposite leg over adjacent leg. So blue leg over brown leg. Okay, there we go. All right, moving on. SOHCAHTOA. So now let's take an example, right? Let's say we have an angle here, theta, and we have an opposite leg of 5. We have an adjacent leg of 12, and we have a hypotenuse of 13. Okay. So what is sine of theta? It's opposite over hypotenuse, right? So that is 5 over 13. Again, opposites relative to theta. What about cosine of theta? That is adjacent over hypotenuse. So it's the adjacent leg over hypotenuse, aka 12 over 13. And what about tangent of theta? Tangent of theta is opposite over adjacent. Again, opposite leg over adjacent leg. So that again here is 5 over 12. Okay. All right. Let's keep it moving. Now, another cool thing that they like to test on is that sine of an angle is equal to cosine of the complement, and vice versa. Cosine of an angle is equal to sine of the complement. So if we get this with actual values, we can see that sine of 10 is equal to cosine of 80. Again, complements add up to 90. 10 and 80 add up to 90. Makes sense. Okay. Sine of 30 is equal to cosine of 60. Sine of 45 is equal to cosine of 45, and so on and so forth. Now, how is this usually manifest on the test? Well, usually from what I've seen is they'll be like, all right, remembering that sine of an angle equals cosine of the complement. If I'm given this triangle, where I know it's a right triangle, what do I know about A and C? Well, as I mentioned before, if it's a right triangle, that's 90. These two have to add up to 90, meaning A and C are complementary, which means sine of A is equal to cosine of C, and sine of C is equal to cosine of A. That's usually how it shows up in the SAT. So you want to, it's not just always about the numbers. It's also about a triangle, a right triangle in particular, and recognizing that the two acute angles are by definition complementary. Okay, circle theorems. Here we go. So when we're talking about circle theorems, we're just going to do some terminology real quick. So circumference is the length going all the way around. Center of a circle is, of course, the center of the circle. We have radius, which is the length from the center out to the edge of the circle. We have the diameter, which is going all the way across from one edge to the other edge through the center. We also have a chord, which goes from one end to the other. Now, you might say, well, wait a minute, a diameter goes from one end to the other. Is a diameter a chord? Yes, it is. It's just a chord that goes through the center. We also have a sector, which you're going to also have to know how to get area of a sector, which we're going to talk about. And that's like a pizza slice, right? Slice of pizza. And then we have a secant, which is a line that goes through the circle. It penetrates it, versus a line segment. And then we have a tangent, which touches it at one point. And also, notice that we're going to talk about this in more detail later. This is very important. They love to test on this. A tangent to a circle at the point where the radius touches it always forms a right angle. And then we have a segment, okay? A segment is like if you draw a line straight across, it's that area in that little curvy part, okay? If you could take like this sector, for example, and draw a line straight across and like isolate the tip of that sector, and that's a segment. All right. Okay, so what are my formula? Again, this is on the reference sheet, but what are my formulas to calculate circumference? 2 pi r. And area, pi r squared. Again, all about the radius. What about arc length? That's a little chunk of the arc, okay? So it's, again, a fraction of the circumference. No circumference here, circumference is here too, but now you're taking a fraction, which is just the interior angle, divided by 360. Why 360? Because 360 degrees is what goes all the way around. All right. Yeah, so Cole is asking about surface area. So it's a little overkill what I went into in surface area. What I've seen is really surface area of prisms. And those, even though there's a formula for it, you can deduce it on your own. You can be like, all right, what are the faces of this rectangular prism? Oh, there's 6 of them. They're all rectangles. I can calculate the area of each of them individually and add them up. I'm putting it there in an abundance of caution just in case, because I see these surface area questions. You know, it's like one where they take 2 prisms and they glue them together. If you remember that, I think it's from practice test 4. I'm showing you like a pyramid and a cylinder just in case, because I think they're fair game, even though I haven't really seen surface area problems like that. I've seen surface area of a sphere, but that was on a third-party practice test. Just trying to prepare you. Most important is surface area of a prism, I would say. Okay. And area of a sector is, again, that central angle over 360. Same fraction, but now times the area, pi r squared. Okay, now what is arc measure as opposed to arc length? This can be in degrees or radians. So it's kind of the same thing as arc length, except this is in, as I mentioned, degrees or radians. So, and it's going to be equivalent to a central angle. If a central angle is cutting it out, and you're going to see what that looks like in a second. Or it's double an inscribed angle if that's what's cutting it out. So what am I talking about? Let's say here I've got arc AB. What's the arc measure of arc AB? It's 50 degrees. And that is the same as the central angle AOB. So AOB is 50. And this arc measure that it's cutting out is also 50. Okay? So that's pretty straightforward. That's kind of makes pretty logical sense. Now, if we look at an inscribed angle, meaning an angle starting on the circle, we draw 2 lines out here, inscribing that. Now, whatever that arc length is going to be, it's going to be double whatever the inscribed angle is. So, for example, if my angle is 25 degrees, that's the inscribed angle. The arc length is double that, which is 50. So you notice, right, these 2 arcs are meant to be like the same exact size, these arc measures. And then the angle, you can see that this is inscribed, and it clearly does look smaller than that one, about half of it. All right. Circle tangents, okay? So this is, again, the thing that I was talking about before. A tangent line to a circle is always going to be perpendicular to the radius that it touches. So, for example, if I have a circle, here's my center, here's my radius. If I draw in a tangent to that point, it will always form a right angle. Very important. They test on this all the time. All the time. You got an arc length problem wrong because it was a semicircle and I did it over 180. And so, oh, yeah, that's a tricky one. I'd love to see that problem if you could send it to me. And then the other thing to note, which I saw recently, I think on practice test 5 or 6, I think 5, external tangent segments from the same point are congruent. Okay? And what does that mean? Well, here's a circle. Here's an external point. Here are two tangents. And they are tangent to the circle, meaning touching at exactly one point. And if I have these two tangents from the same point, they're congruent. They're equal in length. Very important. And they kind of look equal in length, right? So you can sort of make that assumption if you're not sure. And once again, if they are, of course, tangents, they are perpendicular to the radii that they touch. So those, again, form right angles. Okay. Now we're on to subcategory 5, unit circle trigonometry. Okay. People have asked me before, do I need to know the unit circle? I say no. But it's not bad if you know it. It's helpful, but there's ways around it. We're going to talk about that. Wait, but isn't a semicircle? Yeah, it's semicircle is 180 degrees, but it's like, but it doesn't change the formula for arc length. Like if you have an arc within a semicircle, you're still going to use your traditional arc length formula. It's like, how can I explain it? Okay, think about it like this. If you have a circle, right, and you have like a 30-degree angle coming out from the center. So you're going to do 30 over 360, right? Now, if you chop half of that circle off and you just have the upper semicircle, it's not like the arc changes, arc length changes, or the arc measure changes. It's still 30 degrees arc measure. It's still whatever arc length it was. You get what I'm saying? So even though it's like could be a piece of a circle, you're still using the exact same formula because it stems from the same premise of originating in a full circle, hence being out of a full 360 degrees. All right. So unit circle trigonometry. So now where we get to, what matters now is the signs. Okay, this was much more prevalent, I'd say, on the older version of the SAT, the paper version. But what you want to think about is you're going to have a lot of repetition in these values. The thing is now that you can always use a calculator, it changes the game. You don't have to have this down as much. But depending on the size of an angle measure, you're going to end up in one of these three quadrants. And depending on the quadrant you end up in, it's going to change the sign of your trig function. So for example, in quadrant 1, we have, this is a little acronym to help you remember. Everything is positive. Sine, cosine, tangent, they're all positive. Quadrant 2, S, all students. Why S? Because that tells you that only sine is positive in quadrant 2. Tangent and cosine are negative. Quadrant 3, take, all students take. Why T? Tangent. Only tangent is positive in quadrant 3. And then calculus, that's because only cosine is positive in quadrant 4. Sine and tangent are negative, okay? So again, students matches with sine, tangent matches with take, calculus matches with cosine. Why do I say this is not as important anymore? Because if you're like, wait a minute, is, I don't know, tangent of 300 positive or negative? Well, you can just go to Desmos, and as long as you're in degrees mode, say, what is tangent of 300? Oh, it gives it to you right there. It's negative whatever. So you can quickly tell, oh yeah, tangent in the fourth quadrant is supposed to be negative using Desmos. But this is just a helpful tool if you want to recall it a little bit more quickly. Oh, thank you, Cole. I hope I explained it okay. All right, so again, this shows us that sine of 120 is in between 90 and 180. It's in the second quadrant, hence sine would be positive. Sine of 195 would be negative because now we're talking about the third quadrant. Only tangent is positive there. Tangent of 220, we're in the third quadrant, but tangent's positive in the third quadrant, negative in the fourth quadrant, right? 330 is in here. And cosine of 335, again, fourth quadrant, that's positive, and anywhere else except for the first quadrant, so this is second quadrant, 135, is negative, okay? And same for those equivalent radian values. All right, so here's the unit circle that people are asking about. The reason why it's not as bad as it looks to memorize is because the same three values are everywhere, just repeated. Rad 3 over 2, 1/2, rad 2 over 2. And then it's just the distribution kind of changes, and the signs might change, but it's pretty much those three numbers. And then 0, 1, 1, 0, 0, negative 1, negative 1, 0. Those are pretty easy to plop in there at the end. But anyways, how do we use the unit circle if need be? Sine of any angle is equal to the y value of the corresponding coordinate. cosine is equal to the x value, and tangent is the ratio of the y over the x. So how does this look in practice? If you're saying, hey, what's sine of 45? Oh, my y value of 45 is rad 2 over 2, hence sine of 45 is rad 2 over 2. What about cosine of 150? Here's 150. Cosine would be that x value of negative rad 3 over 2. What about tangent of 240? That's rad 3. Why is that? Because if I go to 240, it's negative rad 3 over 2 divided by negative 1/2. Negatives cancel out and it becomes positive rad 3. Final category, guys, we are into circle equations. Here we go. What is standard form for a circle equation? X minus h squared plus y minus k squared equals r squared. Okay. Now, what are all the different parts here? H, K make up the center, and R, not r squared, R is the radius. Okay, so if I have a circle here, HK is the center, and there's my radius. Now, let's see what this looks like on Desmos, just so you can get an idea. We'll say, we'll say x minus a squared plus y minus, actually, let's say k squared. We'll say h and k equals r squared. Okay, let's do h and k just like I have on the slide. Now, r we said is the radius, right? So right now r is 1, radius is 1. R is 2. Now this side would be 4, but the radius is 2. You see the radius grows as this r value grows, and it shrinks as it shrinks, okay? Now, what about h and k? Now I said h is the x value of the center. Now right now it's 1, 1. So the center is at 1, 1 right there. But now as I change this value, the h value, look, it's moving to the right. Right now the center's at 8, 1. Okay, likewise, as the r value changes, as not the r value, excuse me, as the k value goes up, center moves up, right? You see now the center's at 4.5 comma 8, bring it back down, etc. Okay. Next, we got the circle equation down here. So what if we get something like this? Well, we can tell a lot about this circle. For example, I can tell that the center is at 3 comma 4. And notice it's x minus 3, so it's the opposite. Y minus 4, opposite. Radius is radius squared is 25, which means the radius is the square root of 25, which is 5. So that's pretty cool. And now if we look at the graph, right, we've got a radius at a center at 3, 4, radius of 5 units. Okay, cool. But what happens if we get something like this, not in standard form? What's the center? What's the radius? I don't know because it's not in standard form, right? Radius is not the square root of a negative 11, obviously. But we can get it into standard form. Now, this is the old school method. There's a new method that you can use Desmos, which is a lot well, not faster, easier, I'd say, if this is a pain for you. But this is actually faster if you have it down, in my opinion. So how can we get this into standard form? We got to complete the square, okay? So we group the x's and the y's, if you remember this from math class. We take this term here, 4, divided by 2 and square it. 4 divided by 2 is 2, squared is 4. Take this term, negative 8, divided by 2 is negative 4, square it, which is 16. And we're going to add 16. But notice I'm adding 4 and 16 to the other side as well. Why? Because we always have to do that to keep the equation balanced. Now, the beauty of this is that this is now a perfect square. So is this, right? And that's why it's called completing the square. We're creating perfect squares. Now I can factor x squared plus 4x plus 4 into x plus 2 times x plus 2. This one is y minus 4 times y minus 4. Condense it as follows. Guess what? Now I know my center is negative 2, positive 4. Again, the opposites of those two. And my radius is a square root of 9, which is 3. So check it out. Negative 2, 4, and a radius of 3. That's how you do it. Okay. Now, the other way, I don't know, my animation got messed up. But anyways, now what's the other way that we can do this? Okay, well, once again, we have this crazy equation. Yeah, I could complete the square, but if you forget how to do that, well, let me just plug it into Desmos as is. Check this out. I wrote it in exactly as is. Nothing fancy. And it gives me the circle. Amazing. Yeah, but I don't know the radius. It's hard to tell. I mean, I can kind of guess. I can eyeball it. But if I just click the top and the bottom points, look at that. The coordinates pop up. That's the exact top and the exact bottom. Well, if I want to calculate the radius, since these x's are exactly aligned, the difference of the y's is the diameter, right? That's the full length across. So if I want the radius, I take the difference of the y's and half of that, because half of the diameter is the radius. So 7 minus 1 is 6 divided by 2 is 3. There's my radius. What about the center? The center is the midpoint of these two top values. Well, I already know the x is going to be -2 because the middle of -2 and -2 is -2, right? But what about the y values? It's the average of those two y values. 7 plus 1 is 8, divided by 2 is 4. So my center is, oops, I wrote 3. It's 2, 4. Little arithmetic mistake. My bad. Okay, fixed it. All right, we're back in business. All right. So there we go. -2, 4, boom, done. Okay. Oh, that's my last slide. We're done. We're done. Amazing. We're just at the top of the hour. So let me see if we've got any other questions. Otherwise, I might end this. Yeah, we don't have too many other questions. Guys, thank you so much for joining. This was a blast. And we are done with the critical concepts. We've gone through everything. So if you've been following along, taking notes, taking the quizzes, doing your thing, and there's going to be a quiz for this one posted by tomorrow, you're good. You should know everything you need to know at this point for the math on the digital SAT. Now, if you're up on the practice, I got to post the video explanations for the last practices. I haven't done that yet. I was supposed to post that on Sunday. My bad. I'm going to post it right after this. But anyways, watch my videos, watch my walkthroughs, especially if there's any problems that stumped you or tricked you or whatever. It's going to be super important. And that's it. Thank you guys so much for joining. Once again, if you're looking for amazing digital SAT practice tests, look at the SAT Crash Course. You can see the banner at the top, 20% off if you use the code SCALAR. And one more time, join our digital SAT platform, School. It is amazing. It is growing. I think I can say that it is the best online community on the planet. Free SAT prep for the digital SAT. Pretty confidently say that. So make sure to join. All right. That's it, everybody. Thank you guys so much for joining. I really appreciate it. Thank you for the love. Thank you for the likes. Thank you for the comments. Thank you for the engagement. Thank you for joining along. Much appreciated. And I will see you in the next video. Take it easy.